Use the functions f of x is equal to 2x plus 3 and g of x is equal to x squared minus 4 to find the following. So here we are looking at algebra with functions. And part A is asking us to find the sum of two functions. So we have f plus g of x. And so we know this, of course, separates to f of x plus g of x. And we can go ahead now and plug our given functions in. So we have 2x plus 3 for f of x. And now we're adding g of x, which is x squared minus 4. And to simplify, we want to combine up our like terms, which gives us a beautiful final answer of x squared plus 2x minus 1. And the order in which you write your final answer here does not matter. I have my terms in descending order, but any order is okay, as long as your algebra is accurate and consistent. In part B, we are asked to find the difference. So we have f minus g of x. So this is going to separate to f of x minus g of x. And because we're taking the difference here, let's be careful and make sure that we include brackets or parentheses around g of x. And this is to remind us that we need to distribute that negative sign through. So we have 2x plus 3 minus x squared minus 4. And so again, those parentheses remind us to take this negative and distribute it to both terms, which leaves us with the beautiful final answer. Well, not the final answer, not quite yet. So we have 2x plus 3 minus x squared. And then a negative times a negative leaves us with plus 4. So grouping those like terms together again, we are left with the beautiful final answer, minus x squared plus 2x plus 7. In part C, we are asked to find the product. So we have f times g of x, which by definition separates to f of x multiplied by g of x. And plugging our given functions in, we have 2x plus 3 multiplied by x squared minus 4. And now we'll apply that foiling method. So we have 2x times x squared, which will give us 2x cubed. We have 2x times negative 4 for a minus 8x. We have 3x squared, or 3 times x squared for a plus 3x squared. And then we have 3 times negative 4 for a beautiful negative 12. And now actually looking at these terms, we don't have any like terms, so we can just box this up. This is our beautiful final answer. So we need a little bit more room. So part D is asking us to find the quotient and the domain. So we have f divided by g of x, which by definition separates to f of x divided by g of x. And we know, of course, this is such that the denominator cannot be equal to 0. So plugging our given functions in, the numerator is 2x plus 3, and the denominator is x squared minus 4. And so you could box this up as your answer for the quotient, but notice also that the denominator is a difference of squares. We have this as x squared minus 2 squared. So we can also further rewrite this as 2x plus 3, and that is all divided by x minus 2 times x plus 2. So either form here is perfect for the final answer of the quotient, but in particular, this second form is going to be helpful in finding the domain. So of course, we know that the domain of a rational function or a fraction function cannot have 0 in the denominator. So our denominator cannot be equal to 0. So we're going to go ahead and set that factor denominator x squared, or x minus 2 times x plus 2 cannot be equal to 0, and we want to solve for x. So applying that 0 factor property, we have two cases to consider. We have x minus 2 cannot be equal to 0, And we also need to think about where x plus 2 cannot be equal to 0. And in case 1, if we add 2 to both sides of the equation, the 2's will cancel each other out, and we are left with x cannot be equal to positive 2. Similarly, in case 2, if we subtract 2 from both sides of the equation, 2 minus 2 goes to 0, leaving us with x cannot be equal to negative 2. So these are the two undefined values of our domain. And if we think about a number line here to help us with our interval notation, we have, so here is our beautiful x-axis. And we know, of course, as we move to the left-hand side, this is where x is moving towards negative infinity. Moving to the right-hand side is where x is moving towards positive infinity. And we only need to focus on these two undefined values. So we'll say right about here is negative 2, and here would be positive 2. And we want to be sure to include holes at those points. So open holes at those points because x cannot be equal to them. So there's our open holes. So we can see here that x can be any real number except negative 2 and positive 2. So we're shading in that region in between those x values. And so therefore our beautiful final answer here in interval notation, x can go from negative infinity to negative 2, using that round parenthesis to exclude that x value. Now we unite this with the interval from negative 2 to positive 2. Again, using round parentheses to indicate that x can get infinitely close, but cannot equal 2. And last but not least, we unite this with the interval from positive 2 to positive infinity. And so this is our beautiful final answer here for the domain of the quotient. So a little bit more room. So we can now go ahead and find the compositions. So part E asked us to find f of g of x. So we know by the definition of the composition that we're going to go ahead and substitute the function g of x into f. So I think that this notation can be a little bit confusing, so I'm just going to rewrite this as f of g. And now let's keep in mind here, we know, of course, we are given f of x is defined as 2x plus 3. So to find f of g, we're now going to go ahead and replace each one of these x's with the function g. So this tells us that f of g is going to be equal to 2 times g plus 3. And for safety here, let's incorporate parentheses around g, especially because we have that scalar multiple, or that constant multiple of 2. So now we can go ahead and we'll plug in that g function. Remember that g of x is defined here as x squared minus 4. So plugging that in, this is now 2 times x squared minus 4 plus 3. And we can simplify. We can go ahead and distribute 2 through to both terms. And this becomes 2x squared minus 8 plus 3. And we can combine those two like terms. We have negative 8 plus 3 for a beautiful final answer of x squared minus 5. And last but not least, we have the reverse of this. We now want to go ahead and find g of f of x. So again, by definition, we are going to substitute the function f of x into g. Or again, we can think about this as g of f. So again, to help guide us in what to do, we'll keep in mind, of course, that g of x is defined here as x squared minus 4. So just as we did above, to find g of f, looking at the original g function, we're going to replace each one of these x's with f. So here we go. This is going to be equal to, or we can say that g of f is going to be equal to f squared minus 4. And now plugging f in, this becomes 2x plus 3 squared minus 4. And now we can go ahead and simplify. We can expand that binomial product. So this is equal to 2x plus 3 multiplied by 2x plus 3 minus 4. And we'll FOIL these terms out. We have 2x times 2x for a 4x squared. We have 2x times 3 for plus 6x. We have 3 times 2x for plus 6x. And last but not least, we have 3 times 3 for plus 9. And we see we have two like terms, or the two intermediate terms are the like terms. So this will become 4x squared plus 12x plus 9, and don't forget that minus 4 on the outside. So we can add up our two constant terms, and this leaves us with the beautiful final answer of 4x squared plus 12x plus 5.